Good morning, grade 8. We are now in the middle of topic, atomic structure.
Good morning, sir.
Let me share my screen. Again, let's have a brief recap of what we had done last meeting. Okay, we discussed about the history of uh, how um, these elements discovered through the electrons, protons, and neutrons. The arrangement also of this in the orbit of an element. What else? We discussed also um, about the atomic models. We also discussed about how to get the number of protons, the number of electrons, and the number of neutrons in a particular element. Okay. Again, to get the number of protons, you need to check the atomic number because protons is equal to its atomic number. Like for example, I have here the periodic table of elements. Let me share my periodic table of elements. Okay. Can you see my shared screen? All right. I have only two students.
Yes, sir.
Where are the others? Oh, you cannot blame me with this, huh? I already discussed this 2 times already. Okay. Again, when you're going to look at the protons, the number of protons in a particular element, you need to check on the atomic number. That's the number of protons. Okay, atomic number, like for example, aluminum has 13, silicon has 14, phosphorus has 15, what else? Beryllium has 4, lithium has 3, neon has 10. So those are the number of protons. How about the number of electrons? In order to get the number of electrons, you need to get the atomic number minus the charge. Okay? Atomic number minus the charge if it is cation or anion. Okay? Like for example, ferric chloride, ferrous or ferric. It's a ferric. Ferric is negative 3. Di ba I discussed about negative minus negative? It will become positive. Okay? Let's have this one. Let me share again my screen. Looking at the periodic table, ferrous has or iron has 26 protons. Okay? Fe, let's have this one, minus 3, and Fe plus 3, 26, and let's have ferrous 56. Ferrous 56. Okay. If you're going to look at it, this is the correct way on writing it. Okay. The lower part or the lower part of the element is called your atomic number. The upper part is your atomic mass. Okay. We choose 56. Remember that there are a lot of variety of ferrous or iron. Okay. From 55.85, from 55 to 55.85. Let's have 55. Let's change this one to 55. Let's have 55. Okay. So let's have ferric chloride and ferrous. Okay. In getting again the protons, how can you get protons again? Grade 8? Any idea? Grade 8?
No, sir.
Are you still with me? Again, how can you get again the protons of
Yes,
the
sir.
element? How can you get the protons of an element? Robbie? Are you still with me? Can you still hear me? Okay, how can you get the protons of an
Yes,
element?
sir.
Huh? Robbie?
The amount of protons, sir.
Yes, the number of
The
protons.
amount of protons. The amount of protons.
Yes.
It's equal as the atomic weight.
Atomic weight? Atomic weight, Robbie?
Yes, sir.
Was it the atomic weight?
Yes.
I didn't discuss about atomic weight. About the number of protons in the atomic weight?
I know, sir.
Huh?
Is equal I to the atomic number.
That's the
To the
atomic
atomic
number.
number.
This 26, right? Because this is equal to the atomic number,
Yes, sir.
correct? This two, this is an ion, and this is cation. Okay? These elements also are called what? Elements with the same atomic number but different atomic mass is called what? What was that again? Elements that are with the same atomic number but different atomic mass is called is called
Isotopes, sir.
isotopes. Yes, these are isotopes. Okay, going back, how can you get our electrons, the number of electrons? how can we get the number of electrons? EM. EM? Did you get the lesson? Did you understand?
Yes, sir.
Okay, how can we get the number of electrons? How can we get the number of electrons?
It's equal to the atomic number, sir.
Atomic number and
And
atomic
but
number?
I don't know anymore, sir.
Huh?
I don't know anymore about
Huh, you
those.
don't know anymore? Di ba minus the charge? Di ba minus the charge? Nasabtan? Magbinisaya tabi nasabtan eh. Nasabtan? Wala. Di ba the electrons is the atomic number minus the charge? Everyone, hello?
Sir?
Di ba I discussed this one last time?
Yes, sir.
Okay. So what happened? Huh? Okay. Di ba I discussed just a while ago also? In in order to get your electrons, it is your atomic number minus the charge. Di ba? Grade 8, we have actually a lot of activities for this. Asa dapita naglibog? Grade 8. Janine and EM. Vincent, are you still with me?
Yes, sir. Yes, sir.
EM. How about Janine? How about Janine? Okay. In order to get your electrons, it is actually the atomic number minus the charge. Since the charge here is negative 3, okay, 26 minus negative 3, it will become positive. Minus the negative symbol, it will become positive based on the integers, integral properties. Diba? So 26 plus 3, it will become ila?
29.
29. Correct. So the number of electrons is 29. Sure, why 29? 29 because this is an ion. What is the definition of an ion? It is a kind of ion that has more electrons than protons. Since it has more electrons than protons, it is electrically or negatively charged. That's an ion. Okay? How about how to get your neutrons? How to get your neutrons? The number of neutrons? This is
Mass number.
the atomic mass, okay, or mass number, and then next EM minus
Mass number minus atomic number.
the atomic number, which is 26. Okay? 55 minus 26, it is 29.
39, 29.
This is 29.
Is it? No?
Okay. So we have 26 protons, 29 electrons, and 29 neutrons. How about in the cation Fe plus 3? Protons, electrons, neutrons. Okay? Again, your protons is equal to your atomic number, 26. Your electrons is equal to atomic number minus, okay, positive 3, which is your charge. Okay? Is equal to 23. Your neutrons is atomic mass or mass number minus your atomic number, 26, is equal to 29. So our protons for Fe plus 3 is 26 protons with 23 electrons and 29 neutrons. Do you have any questions so far? But sure, how about there's no charge, or it is not an ion or a cation? It is as is. So the number of protons is equal to the number of electrons because it is balanced. Okay? Wala kay minus, wala may charge. The ruling is, if there are some charges, you deduct the charges to the electrons or the atomic number. Question so far? Questions?
No.
Answer.
Okay, let's forward. Forward. Let me share my screen again. Did you get the point? Did you get the idea?
Yes, sir.
Okay. Again, let's review, a recap. The number of protons is equal to its atomic number. The number of electrons is the atomic number minus the charge. If it is neutral or if it is not an ion or a cation, tendency is the number of protons is equal to the number of electrons. How about the number of neutrons? This is the mass number minus the atomic number. Well, let's move forward. In writing chemical symbols of elements, a superscript and a subscript are often seen in the left side of the symbol, just like what we did a while ago. Superscript refers to the mass number in the upper part, while the subscript refers to the atomic number in the lower part. Studies on masses and atoms show that atoms of the same element have different masses, such as the species called isotopes. Correct. The one we had discussed also a while ago. Isotopes have different mass numbers, thus they also differ in number of neutrons. However, the variation in the number the variation in the number of neutrons does not change the identity of the element. This is because isotopes of a particular element have the same number of protons. Remember that the number of your protons is equal to your atomic number. The discovery of isotopes contradicted Dalton's postulate that all atoms in a given element are alike. There are about 250 isotopes occurring naturally, and more than 1,000 are made in nuclear reactors. That is why they are usually radioactive. Okay. Isotopes are found in extensive application in medicine, like cobalt-60 is used for cancer therapy, and iodine-121 is used for greater therapy. However, an atom may have a charge. The one that I'm telling you a while ago, if an atom has more electrons than protons, the species becomes negatively charged, or an ion. If an atom has less electrons than protons, the species becomes now positively charged, or cations. Charged species in general are called ions. Okay. Then adequacy of Rutherford's model. Remember that the experiment of Rutherford gives us an idea that um, we can actually split atoms into sub-molecular components. Okay. Rutherford's nuclear model of atoms suffered major flaw. It con it conflicted with previous established theory of electric field proposed by Scottish physicist James Maxwell. That's around 1831 to 1879. When a charged body moves in an orbit around another oppositely charged body, the assembly of particles gradually lose energy by emitting radiation. The loose energy would cause the electron to move and circle even closer to the nucleus until eventually these electrons would be directly in contact with the nucleus. Remember that your nucleus is positive, and the one moving in around the nucleus are negative. So it is really what? Attractive, or they get attracted to each other. The dilemma remained unresolved for same time. It was desperate situation, but Niels Bohr in 1885 and to 1962, he is actually a Danish physicist, provided the answer. How? Let's tackle later how Niels Bohr answered the problem. Okay, he actually explained the scenario. Nature of light. Light has always fascinated man. The first scientific study on nature of light was done by Christian Huygens in 1629 to 1695. He is actually a Dutch mathematician and a physicist. He stated that light, like sound, is a wave motion. His idea of the wave nature of light met much opposition. Sir Isaac Newton in 1642 to 1727 was one of the giants in science. Remember that Newton also established already the laws of motion. Okay? Who opposed this idea? Newton formulated the corpuscular, or the particle theory of light. Okay, according to his theory, light is made up of very fast and very small particles which travel in a straight line. Maxwell predicted that an alternating current in the circuit would radiate energy in the form of electromagnetic waves traveling through a vacuum at the speed of light. Maxwell also wrote, if it shall be found that the velocity of the propagation of electromagnetic disturbances is the same velocity of light. We have strong conclusions for believing that light is an electromagnetic radiation. Later on, Heinrich Hertz in 1857 to 1894, he is actually a German physicist. demonstrated by experiment the electromagnetic nature of light, thereby confirming that Maxwell's interpretation. At the beginning of the 20th century, Max Planck and Albert Einstein used the particle model to explain some properties of light, which could be explained by the wave theory. So, from Christian Huygens going to Sir Isaac Newton, which actually created corpuscular or the particle theory of light, going back to Maxwell and to Henry Hertz or Heinrich Hertz. Okay, Heinrich Hertz actually discovered the um the hertz actually named after him. No? Hertz, megahertz, kilohertz, those are actually from the name of Heinrich Hertz. Let's take a look at more further. What are the contribution of Heinrich Hertz all throughout the process? Max Planck considered the electromagnetic radiation emitted by glowing objects to occur in pockets or pieces. He called the pockets of energy as quanta. That is their quantum. Okay? Quantum came from quanta. Einstein called the discrete energy as pockets or as pockets as photons. Okay? Photons means light. Do you have any questions so far? This is in recognition of kind of
No, sir.
the quantum physics. The quantum physics came from this, from quanta and photons. Okay? Quantum physics says that objects can have a certain particular energies. Einstein theorized that electromagnetic radiation like light has a characteristic of both a wave and a stream particles. So again, the role of Heinrich Hertz there, he actually discovered the frequencies of these electromagnetic waves. Wave particle duality of nature. The wave particle duality of nature states that particles act like waves and waves like particles. However, a massive particle has less wave properties while a particle little mass like an electron has more obvious wave-like properties. Remember that your electron also move just like a wave, but it is a wave-like. It is a wave-like. Obviously, you can actually observe this one to the experiments. Bohr's model. Let's stop the discussion in wave-particle duality and let's continue the discussion by next meeting. Hopefully, by next meeting also, we can do the protons, neutrons, and electrons. Please prepare for a prepare for your periodic table of elements, and we'll be checking on the number of protons, neutrons, and electrons of some particular elements. Right? Do you have any questions so far?
No, sir.
Okay. Did you understand the concept? Or we are too
Yes,
fast?
sir.
Are you sure?
Understood, sir. Yes, sir.
This will come out in your major exams. Pretty sure. Alright? If you have questions, please drop it by in our GC or you can actually send it to me via a private message. Right? I think that'll do for today, class. Thank you for
Okay, sir.
Ethan, Robbie, EM, and Janine. Have a nice day, grade 8. Goodbye.